Hello, everyone. Welcome to my talk. I'm Jing Tang from National University of Singapore. And I'm so glad to share with you our recent work regarding monotone submodule maximization with the Knapsack constraint. This is a joint work with Xue Ye from Nanyang Technological University and Zhu Chongse from AUS, Kai from the University of Science and Technology of China, and Jun Song from the University and Buffalo. And so today I want to first introduce you some basic knowledge, basic background of this problem. Then I will discuss our main results, say the multivariability algorithm can achieve approximation ratio of 0.405. After that, I will show you our second results. We derive some data-dependent upper bounds to help derive some beta approximation ratio empirically for the gradient algorithm. Finally, a short summary will give and with some discussion on future work. So a submodular set function, it maps a set to a real value. And we define the marginal gain of element to a set S as the gain of adding this element to set S, okay? So the submodular function just says the marginal gain of adding an element to a smaller set is larger than that of adding it to a larger set. It just shows the diminishing returns in the economics or in the daily life. For example, there are two sets, S and T. The yellow part is S, the blue part is T. So if we add an element V to the yellow part, the green part is a marginal gain. If we add the same element to a larger set T, you can see that a part of the green part is covered by the blue part, so the marginal gain reduces. This is the submodular, or say diminishing returns, very simple concept. So let's see some examples that are shown to be submodular. For example, the coverage function. Alice loads A, B, Bob loads B, C, then together they load A, B, C. Very simple, right? Both load two elements, but together just 2 plus 2 is 3. Okay. And another example is the facility location problem. The facility location problem, the objective function or say the benefit function is shown to submodule. And in the information theory, the entropy or mature information, these functions are also known to be submodule. And then simply saying the submodule function is a discrete concave function, such as the square root function, such as the logarithm function. So you can imagine that many functions are discrete concave functions. So of course, there are many examples. And in this work, we look at the MSK problem. So we consider the function is the monotone function, which means we add an element, always increase the objective function. And the monotone submodule maximization with the Knapsack constraint, it aims to maximize a monotone submodule function and subject to cost within budget. The cost function is the Knapsack function. And actually, in many AI or machine learning applications, these they are shown to be submodular maximization or actually MSMK, such as sensor placement, feature selection, value marketing, and so on. So how hard is this problem? Of course, it's hard. Not exactly hard, even harder, that is, very low polynomial algorithm that can achieve approximation factor even exceeding 1 minus 1 divided by E. Remember this factor, this is the best factor. And so some naive algorithm they propose, people may think, okay, we just naively maximize the ratio of the objective per unit cost. This is very naive thinking. Unfortunately, here is a simple example. We can see that the algorithm has no guarantee. It can perform arbitrarily worse. So a question arises that is there any good solutions? That means, can we construct some approximation algorithm that has some constant factors? Here are some efforts. In fact, this algorithm can achieve optimal approximation factors. Unfortunately, we can see that these factors has high time complexity. Even recently, 2019, after this problem explored for near 40 years, the solution is still very high time complexity, which depends on the epsilon parameter. So this time complexity makes these algorithms impractical. So another solution is called the multivariability algorithm. This algorithm is proposed in the very early study of this problem in 1982. And the people find that if we simply modify the greedy algorithm that says that first, okay, we construct the solution SG by the greedy heuristic, then we construct another candidate with a star that maximize the singleton state. Then we compare the two solutions. We choose the better one. Okay, this is very simple, right? Simple and elegant, but this algorithm can achieve constant factors. In 1982, this factor is 0.357. And after 15 years later, could find that this factor can be improved to 0.393. Okay, this is very good. Then people will cite this work and refer to this result. Nearly 1,000 papers have cited this result. But unfortunately, there is a long-standing misconception. After another 20 years, people find that the proof for this factor is wrong. How disappointed people are, because many people think this factor is no doubt is correct, but today we find that this factor is wrong. Okay, so a very important question comes. Is this factor still valid for this algorithm? Although their proof is wrong, but is this factor is correct? Okay, so in this work, we are going to answer this question, and the answer is very short. Yes, the factor is still correct, and in fact, we even improve the factor to 0.4. And this is the first factor better than 0.4. Oh, so this is our main result in the theorem. And here is our high-level analysis approach. We first derive some relations between the solution value and the optimal. Then, based on these relations, we construct an optimization problem involving the approximation guarantee, leveraging these relations. After that, we can obtain a lower bound on the approximation by solving this problem. So this is our key idea. So the key challenge is, how can we construct the relations between the solution value and the optimal? Here is our thoughts. First, we consider the solution Q, which is the intermediate solution obtained during the greedy search. This Q is a solution we construct before we first consider the element in OPT, but not added to SG due to the budget violation. And the second solution we want to consider is the Q prime. Is very similar to Q. It considers the element, second element in OP2, but not added to SG. So conveniently, Q is a subset of Q prime, is a subset of SG. So we can use this relation to guard the relation between SM and OPT. And the third element we said candidate we want to consider is the V star. As I mentioned, another set candidate is V star. So we will also want to compare V star with FOPT. Okay, so for FQ and OPT, we use this relationship. It says for the seed selection construct from the greedy solution, we can use if we do not abandon an element from the T, then we can build this relationship. And then we can construct the first relationship between Q and OPT. After that, we construct the second relationship, Q prime and OPT. This relationship, we look deeper. That is, we find that if the function f is monotone submodular, then the modular function is still monotone submodular. Then, based on this result, we construct the second relations, fs with fq prime and fopt. The third relation is more complicated. A lower contribution here or lower method that we use is to extend the discrete function to a continuous function. Then, based on this extension, we propose a similar result with the previous one. But this is in the continuous form. Then, based on this continuous result, we can construct our relationship between V star and OPT. Okay, now the relations are ready. Then we build optimization problem. Finally, we just solve this optimization problem and get the approximation ratio. Everything is done very perfect, right? So I skipped a lot of details. You may find them in our paper. And although the analysis is not easy to derive, but in high level, the idea is quite clear. So for the second part, in the first part, we prove that the modified gradient algorithm can achieve a constant factor more than 0.4. And now we think, is this factor already tight? Or say, is this factor in the modified gradient algorithm performs just like this factor? Then to answer this question, we propose to derive data-dependent upper bound. Because we do not know the optimal, we compare with the upper bound, we can still get some insights, get some approximation ratio empirically. So here's our idea. Based on the monotonicity and the submodularity of the objective function, we construct a delta function. This function, based on it, we derive upper bound based on any set S. So a key challenge here is how to decide the S, the set function. We think, why not just incorporate the S into the modified greedy solution, or say the greedy solution? Then we just compare the greedy intermediate solution in the greedy search. We find the smallest upper bound, then we prove that this bound is very good. It's within a constant factor of the optimal. Now, we use this figure to help you understand where is the optimal solution, where is our solution value, and where is the upper bound. As you can see, the solution value is between 0.4 and 1 of the optimal. And the upper bound is between 1 optimal and 1 divided by 0.357 optimal. Okay, now let's see some experiments that can demonstrate the tightness of our upper bounds. We use several data sets with millions of nodes and even with billions of edge. Say, Twitter data set, we use the application of viral marketing to demonstrate the MSK problem. We derive the upper bound and we compare the upper bound with the modified greedy solution. Then we derive the approximation ratio by comparing them. As we can see, the blue lines, they are very close to 1. It says two things. First, the upper bound is very close to the optimal. Second, the greedy solution is very close to the optimal also. So this demonstrates that our upper bounds are in fact very tight. And the second experiment, we use the BNB algorithm to demonstrate the useful of our algorithm, our bounds. That is, we use our bounds to cut to filter some branches, and this can be seen from this table. Our bounds can be used to speed up the branch and bound algorithm significantly. So up to several orders of magnitudes. So that's the work today I want to discuss with you. To summarize, first we prove that the modified greedy algorithms can achieve an approximation factor of 0.405. It improves the known factors of 0.357 or 0.316. That's very good. More importantly, it closes the critical gap on the misunderstood factor of 0.393. It even improves this factor, although their proof is incorrect. And the second, we derive some data-dependent upper bounds. These bounds can be used to benchmark to evaluate the solution quality of any algorithms. And the second, these upper bounds can be used to improve the efficiency of some algorithms, such as branch and bound algorithms, to find this exact solution. And in the future work, we are thinking two directions mostly. First question is, although we improve the factors, however, we still do not know whether this factor is completely tight, maybe or maybe not. I don't know. So it remains an open question. Second, this question is even more challenging. That is, can we find an algorithm? Can we design algorithms that can achieve the optimal approximation factor, say 1 minus 1 divided by E, that just use the same time complexity of OM squared? This is very interesting in the theoretical thinking, also in the practice, because if we can construct such kind of algorithms, then we can use such kind of algorithm to solve a lot of real applications. Recall that, as I mentioned, currently all the algorithms that can achieve such kind of factor, they are impractical because their time complexity are very high. So the second question is even more challenging, but very impactful. So that's all today I want to share with you. Thank you for listening my talk, and you're welcome to ask your questions if you have any.